Good morning, team members and Brilliant Aeronautic Security Agency members. We're the intern team from the Logistical Research and Analytics Department tasked with analyzing the provided data from BASA regarding pre-board screening of passengers and crew for all flights departing the nation's airfields, Auckland, Jabocto, St. Francois, and Queenston.
We have been asked to predict the wait times of each airfield. As an extension, we will also explore the optimal number of servers to facilitate serving 95% of passengers within 5 minutes of queuing the system. We are presenting this information to you via recording so we can archive our discussion analysis for future reference and to document our progress.
Firstly, we will address the datasets. The BASA dataset represents information about individuals passing through the airport operated by BASA. It includes a high-level overview of operations at the airfields. The Data P dataset supports the previous dataset by giving us a more precise profile on potential passengers. The Data F dataset is a summary of information on flights from the 4 airports operated by BASA. The Years dataset gives us information over several years and is the same principle as the previous dataset, with the difference of not being focused on passengers and instead on the security profile of several years. Some important variables to highlight include S2, which is the date and time that a passenger scans their boarding pass at the second checkpoint and exits the queue. The wait time, which is the number of minutes a passenger is waiting in the queue between when they scan their boarding pass at the first checkpoint and when they scan their boarding pass at the second checkpoint. And the period of the week, which is the period of the week that the passenger is entering the queue and is classified as either weekday or weekend. From the data available, we are able to see that based on the total passengers per flight and the number of flights included in our data, that we are dealing with just over an estimated 114,000 total passengers departing from the Auckland airfield from September 9, 2028 to December 12, 2028. This estimate can help us understand how many passengers we can expect to complete the scanning process at the Auckland airport. However, this estimate may vary from the true value of passengers for a variety of reasons. Reasons for the true number of passengers departing on a flight from the Auckland airfield to differ from our estimation includes passengers missing their flights, passengers buying an extra seat for their pet so that their pet doesn't need to go in the cargo holder, or for passengers that are removed from a flight. We have visualized the average number of open servers by airfield as compared to the maximum number of open servers. Due to the lack of data pertaining to the small airfields, we are not able to obtain any information on the number of open servers at the Jabocto airport. For the rest of the airfields, we are able to see that the Queenston airport has by far the most number of open servers on average, as well as the highest number of open servers open at once. While this may speed up the Queenston queue wait time, Queenston may have issues with additional costs due to a large number of open servers that may not be receiving enough passengers to justify the cost. The St. Francois and Auckland airfield have a similar average number of maximum servers. However, Auckland Airport does have a higher number of maximum servers open at one time. We have visualized the amount of data we have for each airfield. 97.26% of our data comes from the Auckland airfield, and only 2.74% of our data comes from all the other 3 airfields combined, and we will be unable to use these other 3 airfield datasets to conduct meaningful analysis. We will continue our analysis with a focus on the Auckland airport.
Next, we wanted to analyze the wait time for the airport and find the most optimal traveling option. First, we hypothesized that the amount of servers would directly correlate to the average wait time. But as you can see in this heat map, the most optimal wait times occurred when there was only one server. We then assumed that there must be more passengers when there are more servers available. However, this was not the case, as there were more passengers when only one server was available. We quickly realized that there would be other variables that had a larger effect on wait time than average servers. First, we looked into which days of the week had the longest wait time. We discovered that passengers are more likely to experience longer wait times during the end of the week as opposed to the beginning of the week. Next, we took a look at a direct comparison between the wait times during weekends and weekdays throughout the year. Looking at this graph, we found that during the year, passengers will experience a longer wait time when they travel on a weekday. However, in December and January, the wait times will be longer on the weekend. We believe that this could be due to the fact that people are more likely to travel for work during the weekday throughout the year, and more people are likely to travel on a weekend in December because it is the holiday season. It is also important to note that the average wait times appear higher in this graph because we included data from the year's dataset in order to show the average wait times for December and January. Finally, we took a look at the distribution of passengers traveling to each city. From this heat map, we can conclude that most passengers were traveling to either Borrelia, or Vespuccia, possibly relating to higher wait times for passengers traveling to those specific cities. It is also clear that most people prefer to travel during the mornings and afternoons when we compare this graph to the earlier heat graph. Overall, we would recommend that passengers who are traveling try scheduling their flight earlier in the week or on a weekday during the holiday season. We also recommend that the airport use one server more frequently in order to cut costs, as the number of servers did not reduce the wait time.
As requested, we will predict the wait times at each airfield for which we have data using queuing model analysis. In addition, we will try to find the predicted number of servers needed to service 95% of passengers within 5 minutes.
Before taking a look at the tables needed to establish the queuing model, please note that we found out the exact number of days between the 1st August 2028 and the 31st December 2028 to calculate the number of hours and separated the data into weekday or weekend and then into clusters of 4 hours. Let's take a look at our first table and highlight some interesting aspects of flight scheduling and arrival rates. In the triangle hours of midnight to 4 am, there are no arrivals, the calm before the storm. As the day progresses, there's a slight uptick in arrival rates from 8 am to 8 pm compared to 4 to 8 am. Interestingly, this trend holds true for both weekdays and weekends, reflecting consistent travel patterns. Then comes 8 pm to midnight, which is the slowest time, with the least number of arrivals aligning with the goal of airports to ensure passengers arrive at the destination during business hours. Surprisingly, despite varied activities, the overall arrival rates on weekend and weekdays are similar. In a sense, this pattern reveals the intricate dance of human behavior and meticulous planning that shapes our air travel experiences.
From our second table depicting the distribution of active servers, we are able to see that the Auckland airport primarily has 1 to 2 active servers at a time. We are also able to see that the airport does not open more than 3 servers at a time. We will use a calculated average number of active servers to continue our analysis.
We'll now dive into the world of airport wait times, a crucial aspect of our travel experience. Data are absent during the midnight to 4 am time frame, indicating no arrivals and a real lull in airport operations. Longer wait times are observed during the 4 to 8 am and 8 to noon intervals, reflecting increased airport activity during these hours. The quickest wait time occurs during the hours of 8 pm to midnight on both weekdays and weekends. This aligns with the lower airport activity during these periods, as shown in Table 1. Impressively, 45% of travelers experience wait time of 5 minutes or less, and 99% of instances across all the time clusters boast times of 30 minutes or less. Recognizing wait time exceeding 30 minutes of outliers emphasizes the dedication to maintain a swift experience for most passengers. As we dive more into the analysis, we calculated the estimated service rate using the arrival rate and average wait time. Intriguingly enough, we find that the estimated service rate is lowest during the 8 pm to midnight time frame, possibly influenced by the corresponding lowest arrival rate during those hours. Moving on to traffic intensity, which is calculated using the estimated service rate and wait time, we again observe the lowest values during the 8 pm to midnight time frame, aligning once again with the lowest arrival rate. In evaluating cumulative performance, we also found that the majority of passengers experience wait time of 5 minutes or less, as seen earlier.
We can validate this by comparing this table, the estimated performance, with the actual performance found in our wait time data, Table 3. From our tables, while we see a difference in exact performance levels, the numbers are not very far off from each other. We can deduce our MM1 assumption is reasonable, and thus we can move forward. We will now further develop our model so that we are able to use the data to predict the number of servers needed to facilitate serving 95% of passengers within 5 minutes of queuing the system. Firstly, we will create a regression model to allow us to create an estimate of the number of servers. This table illustrates how our regression was calculated. We take our quarterly observations, lambda, and our estimated service rate, mu, and divide them both by the number of servers. We can see from our regression that there isn't a strong trend. We can see generally that our regression line is showing a positive trend, implying that as arrival rates per server increase, the server rate per server also increases. However, it is noted that our observations are not necessarily congregated around the regression line. This implies that our regression may not be as accurate. Why might we have issues with our regression model? Firstly, assuming all calculations are correct, as our previous tables are valid and the numbers used in this regression are the same, there appears to be at least one possible potential outlier on the lower left of the plot that deviates significantly from the trend. This may be greatly affecting our regression. Alternatively, another reason may be the clusters chosen were not as good as a pick for this model. The clusters may have covered too short of a period of time, meaning we may not have enough data points to produce a regression that reflects the data more accurately. Additionally, this regression model may not be a good fit for this data. We can see further why our regression is not necessarily accurate when looking at our service rate, estimates, and performance levels. Here we take our regression parameters and estimate our service rate with regard to our regression, and we calculate the corresponding level curves, the performance rates. We see from our table that our performance levels are very high for each cluster. We see that according to this table, performance levels are very close to 100% for each cluster and time slot. We do see that between the hours of 20 and 24, so 8 p.m. to 12 a.m., the service levels do not reach 100% regardless of the allotted time, between 5 minutes to 30 minutes. This may be because there is only one active server, if at all, on during those hours. Comparing this to our performance rates calculated in the MM1 estimates table 4, we see that our performance rates are different and not as close. This also highlights why the regression model may not be the most accurate. This range of service levels would imply that the majority, if not all, of people that are waiting less than 5 minutes. From this point forward, although we realize there may be issues with our regression model, for the sake of our analysis and goals, we will continue on with our process to predict the number of servers needed to facilitate serving 95% of passengers within 5 minutes of queuing the system with this regression. In order to deduce this, we use the following formula, and we get the following results. Looking at the table, we see that our values for the predicted number of servers are quite small, with 2 values in an undefined range. Our weekend clusters in between 12 p.m. and 4 p.m. and 4 p.m. to 8 p.m. There is a condition that our predicted number of servers must be greater than or equal to 0 and must not exceed the maximum number of servers that exist. In this case, we definitely do not exceed the number of servers in existence, as this is 7 for our data, but we have 2 values below 0. At this point, we cannot make an accurate prediction. This formula is greatly affected by our regression coefficients, and thus if our regression is less accurate, our prediction of the servers will also be inaccurate. To drive this point further, we will check the validity of this by assessing the regression of the average number of servers with the predicted average number of servers. As we can see from the regression model, we see our slope coefficient is less than 1. This is an indicator that there is something amiss in our system and the observations are far from our trend line. What we should be seeing here is a slope coefficient of approximately 1 and that our observations are close to, if not on, our regression line. And what can we conclude from this? Well, our goal was to use the queuing systems analysis to predict wait times of the airfields we have data for. Using the BASA dataset and focusing on the Auckland airfield, we found through our queuing model that our shortest wait time was between 8 p.m. and 12 a.m., 20 to 24 hours for weekday and weekend. This makes sense as our arrival rates were low around this time. The majority of passengers wait 5 minutes or less, and we also see from table 4 that this holds true as our service levels, percent of people waiting less than the given time, are the lowest around 5 minutes. In general, we know the MM1 model provides us with the best quality of service level estimates. To extend our analysis further, we attempted to calculate the predicted number of servers needed to facilitate 95% of passengers within 5 minutes. In doing this, we had run into issues with our regression model, which in turn affected the validity of our calculations down the line. Because of this, we cannot provide an accurate prediction for the optimal number of servers. Where did we go wrong? Our MM1 quality of service estimates appear to pass our validity test checkpoint, and so we can deduce that the issue lies with our regression model. We saw that we may have had issues with either some outliers or our chosen clusters. What could we have tried instead? We could have tried removing our outliers to see how this would affect our regression. Here's an example of what this would have looked like. We can see here our regression line changes and it is now a downward regression. While this may not be incorrect, it still does not compare well with the results of our quality of service estimates in table 4 values. Alternatively, we could have changed our cluster combinations. It may have been that we did not have enough observations for an accurate regression line to be produced. In general, the data will have fluctuations, but by having more data points, this would have allowed us to see a trend line more clearly and properly identify where we would have had these fluctuations. Combinations we could have tried include a seasonal pattern of monthly instead of quarterly to showcase a closer look at the data with more points without disregarding seasonal fluctuations, or a 2-hour time block instead of a 4-hour time. Other issues with accuracy may be around some of our preliminary data processing. The datasets were not all complete, thus we did filter and clean the data. This may have caused an uneven or biased distribution in wait times, loss of crucial data points because of their exclusion, or other issues. Overall, we can conclude that while we were successful in predicting the wait times for our airfield, we were unsuccessful in predicting the number of servers needed to facilitate 95% of passengers within a 5-minute time frame. Key takeaway from this exploration was that while methodology and process may be perfected, data does not behave the way you'd expect it to. A process of trial and error at multiple steps of the methodology and a variety of validity checks help ensure that you are on the right path. It is crucial to consider alternative reasons as to why the data is not behaving the way you did, instead of what you or I as analysts are doing wrong. It may just be a matter of approach.
As we continue our internship, we will continue our analysis of this data and further develop our model to be more accurate. Additionally, as we gather more data on the smaller airports, we will be able to develop unique models for each airport.
We expect the models for each airport to be different due to a difference in size, location, and passenger traffic, which all affect the airport's operational needs. We will return to this video for reference as we continue to develop our models. Thank you.